Okay, so here in this section, we're going to introduce, well, we're motivated here by trying to determine which functions have power series representations, right? And how to find them, right? In previous sections, when we talked about power series, it was really just based on the geometric, right? So we're going to start off by, well, if we did have a power series representation of a function, or what would it look like, right? So we're going to start off here by assuming that the function does have some kind of power series representation centered at A. So it looks something like this. We'll go 3x minus a cubed plus c4 x minus a to the fourth. And let's go one more here. Plus c5 x minus a to the fifth power, right, etc. Okay, so now let's look at what those coefficients would look like, right? So one thing we can do is, well, let's start off by just plugging in values for a. So if I plug in f of a, right, notice that any value that has an x, right, any term there, it's going to be 0. So they all go to 0 except my initial one, c sub 0. Okay, so now we have here, right, how to determine that first coefficient, right, the 0th coefficient. So let's actually now take the derivative of this, right? What would the derivative of f look like? Right now, the first one is just a constant, so that goes to 0. This part here, that just goes to 1, so we're left with c1. And then the rest, it's an application of just the power rule here. 2 c2 x minus a plus 3 c3 x minus a squared plus 4 c4 x minus a cubed plus 5 c5 x minus a to the fourth. All right, and we'll do the same thing here, right? And now instead of f, we have f prime. And let me evaluate this at a. And notice all of these terms that have an x, they go to 0. So we're left with c1. Okay, so now we have what the c1 coefficient would look like, right? It's constant, right? It's just a derivative evaluated at this term a. All right, let's keep going here until we kind of see a pattern arise here. So f double prime of x. Right, so now the first term there is the constant, so that goes to 0. Right, the next term goes to x minus a goes to 1, but we're left now with 2, c2. Right, and then the rest here, we get plus 2 times 3. I'm going to avoid multiplying them for now. Here, and then 3 times 4, x minus a squared. Plus 4 times 5, c3, c4, c5, x minus a cubed, etc. And then we'll do the same thing, right? We'll evaluate now the second derivative at a. So all these quantities go to 0, and we're left with 2 c2. All right, let's do one more, and then we could probably figure out the pattern here. So now the third derivative of x, right now the first term goes to 0, it's just a constant. Then we're left with 2 times 3. And the next minus a is 1, so we're just left with 2 times 3 times c3. And then plus 2 times 3 times 4 c4 x minus a plus 5, well, hold on a second, 3 times 4 times 5 x minus a squared, and etc. We get more of these terms. Again, it's an infinite polynomial, so it just keeps going here. And then we'll do the same thing here, right? F triple prime at A gives me 2 times 3 C3. Right, now solving here for C3, we get C3 is equal to the third derivative at A. Remember, that's a constant, right? It's a function value for the third derivative here, all over 2 times 3, right? Now, one thing to notice here is that if I add this 1 here, right, that is, I mean, I don't change the value, right? It's just multiplication by 1, but I can start to see a pattern here, right? 1 times 2 times 3, that's 3 factorial, right? And you could see if I kept going here, we get multiplying that 1, we get 1 times 2 times 3 times 4, and keep taking the derivative, I would come across that same pattern, right? Even here, right? If you look at this, we get C2 is F double prime of A over 2, but again, you can just multiply in that 1, so it's F double prime of A over 2 factorial, right? And even moving up here, right, you can think of this C1 to be F prime of A, and again, over 1 factorial, right? Think of division by 1, right? Doesn't change the value, right? And just to keep with the pattern here, we could see C0, that is F of A over 0 factorial, right? Which again, we define as 1, okay? All right, so now we could see the general form of the coefficients, right? We could see C sub n to be the nth derivative of A all over n factorial. So those are going to be the coefficients of what we're going to call a Taylor series. So here, let me switch over to our book here. So we see, so now one thing we have to make sure is that, well, in order for that to occur, as we see here in the definition, F has derivative of all orders, right? Now, if it zeroes out, that's okay, right? The derivative of 0 is 0, right? It just needs to be defined at the center of A. And this is what a Taylor series is, right? If you see this here, the coefficients are these F to the n of A over n factorial, x minus A, and then our standard here, power series here, with the coefficients chosen in this particular manner. All right. Now, as it turns out, if you see here theorem 6.6, that if a function f has a power series at A that converges to f on some open interval, then the power series is the Taylor series of f at A, right? So that it is unique, right? There's only one representation there. Okay, so in order for this, and before we move on here, the Maclaurin series, it comes up often enough, right, to kind of simplify our problems here. Whenever A is 0, that's just a specialized case of the Taylor series, but it has its own name. It's called the Maclaurin series, right? So that happens when the x is 0. That's the center of it. All right, so let's take a look at an example here, right? Just a quick example here. And let's say that I want to find the Maclaurin series. And the radius of convergence. Of f of x equals e to the x. All right. Now this one is easy to work with because no matter what the derivative is, right? First derivative, second derivative, 100th derivative, that's always e to the x. All right, and here it's Maclaurin, so that tells me that A is 0. So whatever the nth derivative is at 0, it will always be 1. Okay. All right, so now that we have either the x can be approximated using the power series, right? The formula is f to the n. In this case, it's Maclaurin of 0 over n factorial, and starting from 0 to infinity of x to the n, right? Which is the sum That's just 1, so we get x to the n over n factorial. N goes from 0 to infinity. All right, and now here, let's try to find the interval of convergence, right, or the radius of convergence here, by applying the ratio test. So the limit as n goes to infinity, absolute value x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Right, and then simplifying here, limit as n goes to infinity, x to the n times x times n factorial, and then here I'll rewrite the bottom as n plus 1 times n factorial x to the n. All right, and then if we simplify here, right, x to the n reduce, n factorial reduce, and we're left with the limit as n goes to infinity of absolute value of x over n plus 1, which is 0. All right, so what that tells me is that the convergence does not depend on x, so the interval of convergence is from negative infinity to positive infinity with a radius of infinity. Right, so we have a power series representation of e to the x that looks like this. All right, so here, so we have, just to show you what a graph of this looks like here. So when you see here, the dotted function is e to the x, and in the solid line there is the approximation using a Taylor series. Now, what you see there is just the first term, right? So it's just when n is 1, or k goes to 1, sorry. So it's just the line y equals to 1. Now we can see here, as I'm going to let the series go, so each step of the way it's doing the calculation, right? So it's becoming a larger polynomial. Each k represents now the 20th degree, 21st degree, etc. Right? And we could see that the further out that k goes, essentially the partial sum, right, the closer the approximation is. Right? Really not great once we get out of a certain interval, but the higher that degree gets, right, the more of the convergence that I have, right? Let's kind of checking it out here. Okay, now each one of these partial sums are what are called Taylor polynomials. Okay, and then we'll focus more on that a little in the next few videos here. But this is essentially how we generate power series in this form.